Welcome. We have been talking about functions of two variables. Most of the time we will be given the function as an expression. There are a few situations where you have to come up with the expression for the function by yourself. Many of these involve geometric or mathematical things. For example, things having to do with area or volume where you just use formulas from high school geometry. There are a few business-oriented applications where you have either a profit function or revenue function which you have to find. In some sense, this is similar to what we did in 1130. Revenue is price times quantity, profit is revenue minus cost. There's a small wrinkle if you have more than one product. It's actually quite simple to understand once you know what it is. So let me just do it with an example. Here I have a company making just two models of their bikes. And they have demand equations given in the form price equals something involving the quantities, where the quantities are given in terms of hundreds of bikes sold per week, and the prices are in dollars per bike. And they give us the cost function. We'll also assume it's in dollars based on number of bikes produced. As usual, we'll assume that they produce just enough bikes to meet the demand. Note that the demand functions for each bike involve numbers sold of the two different models. This makes sense because some people might make the decision based on the comparative prices of the two models of the bike. So the price of one will affect the demand for the other. So you get what are called joint demand functions. Now when we calculate the revenue function, we get some revenue from the 10-speed models, some from the 3-speed models. The total revenue is revenue of each of it calculated separately and added together. Of course, when you calculate them, the prices involve quantities of both, so you end up with a function that involves both the quantities. So now let's find the expression based on the given information. The revenue from 10-speed models is the price per bike times number of bikes for the 10-speed bikes, which we are denoting the prices by PA and QA, so that gives me PA times QA. For 3-speed bikes, it's PB, QB. So total revenue is what I get by adding those two. Now it's very much like the one variable case. Substitute from the given demand equations for PA and for PB. This gives me an expression. Now I'm going to simplify this. This is just basic algebra, so I won't go through the details. Do the multiplications, distribute the QA and QB, and then combine like terms. That gives me the expression for the revenue. Profit is still revenue minus cost. So we just take the revenue function we just found, subtract the given cost function, and then simplify. So I have to distribute this minus here over all the terms inside, and then combine like terms. That gives me the profit function. When we're evaluating such functions, make sure you pay attention to the units. In some problems, there might be some twist in the unit. If you read this, you see that quantities are given in hundreds of bikes sold per week. So if you're talking about selling 1,000 10-speed bikes per week, then QA is really 10 because 1,000 is 1,000. 1,500 3-speed bikes means that QB is 15. Now if I substitute this in the expressions we found, then we get the revenue and profit functions. So the revenue is 1,000 10-speed bikes and 1,500 3-speed bikes. It's R of 10, 15. Substitute 10 for QA, 15 for QB for the expressions from the previous slide, and then calculate the arithmetical expressions value. Do the same thing for the profit. Substitute 10 for QA, 15 for QB, and calculate the value. Again, you have to pay attention to units. P's are in dollars per bike, Q's are in hundreds of bikes. So when I multiply them, I get the answer in hundreds of dollars. So if R of 10, 15 is 2750, it tells me the weekly revenue is 2750 in hundreds of dollars. So I should multiply this 2750 by 100 to get the revenue in dollars. Same thing for the profit.